Hello everyone, I hope you are doing well. This is our third session on corrosion inhibition or corrosion protection. So in this session we will cover different computational techniques used for corrosion protection, that how to explore the corrosion inhibition study. So nowadays different organic molecules are used for the coating over the surface of different alloys or metal surfaces to protect them from corrosion inhibition. So in this session I am reproducing these two papers. One is I showing here in the video, and I will show you, I will share these paper with you in the group. So I will reproduce them, that how to study simulation for such type of corrosion inhibition. So initially I am reproducing this one paper, hybrid sol gel coating based on silane amino acids for corrosion protection of magnesium alloys. So actually this paper is both theoretical and experimental, so I am just reproducing the DFT portion. So in this paper I already mentioned about the worth of corrosion study. So you people then study that why we are doing corrosion inhibition study for such type of alloys, etc. So is the author mentions here DFT study for such type of research work. So I am reproducing this portion and will show you that how to perform DFT simulation for such type of studies, and then I will go to the next portion where also the others perform such type of study, but they use also molecular dynamics study, that how to regenerate or how to generate a bulk system, and then we'll study its different MD sites in solvent medium, other the interaction of other molecules with the system. So now I am just recording a lecture on the DFT study. So initially I will share some lectures on DFT, and then we will go to the MD study. So as in this paper they take the magnesium surface, and then they performed the adsorption of different amino acids over this surface. So how they did this study? So this is material studio, and I will be used DMOL code for this study. So initially as I performed already this simulation to save the time, because during lecture performing such type of study will take much time. So I already performed this study, so I will show you that how to perform such study and how to plot different figures. So as I perform here DFT study for the magnesium surface, so this is a periodic magnesium surface is mentioned in the paper. So how you will generate such type of structures? So the magnesium metals are already available in the library of material studio. So just simply go to file and then go to import, in structures you will find a metal folder. So open and then pure metal and select magnesium in them. So different metals are here available. So this is the magnesium. Open this So you will find a unit cell of magnesium metals. This is a unit cell. So is they mention in the paper in deep details that the authors use 8x8 supercell and using GGAPB level of theory to perform such type of simulation, and they applied 3x3x1 K point. So it's go to the material studio and then go to symmetry and extend this structure to 8x8. Create a supercell. So this is a supercell. We just selected 2 layers, so 2 layers are enough to study the adsorption studies, and it will also save our time, because if you select more than 2 layers, then it will be costly to perform such type of simulation using DFT studies. In molecular dynamics you can select more than 2. Then I will show you that how to select those more than 2 structures. So for DFT just 2 layers are enough. Then go to build crystal, rebuild crystal, and apply a vacuum slab of around about 30 angstrom to minimum the reflection between the layers. So this is a 30 angstrom vacuum slab. As the author shows a CPK model in the paper, as you see here, it's a bulk like structure. So you can also represent this like go to display style and select a CPK model. So then you will see it's similar to the paper represented in the figure is the figure represented in the paper. So now it's similar to that one. Okay, so in this way you will generate the surface of magnesium alloy. So I already performed simulation on this magnesium alloy here, but I just selected a 5x5x1 supercell to perform the simulation quickly, because 8x8x1 will take much more time. So I just selected 5x. It's enough for adsorption of a single organic molecule. So then you just go to the demol code and apply all those model as you as we are mentioned in the previous lectures. So for optimization, just select geometry optimization, increase the cycle to 999, and GGAPB use green dispersion correction, use symmetry, and then go to electronic, all electron D and phi 3.5, and then go to more 10 minus 5 is accurate for geometry optimization. Select 999, use DIS up to 6 and smearing up to 0.005, and select K point 3x3x1 is the other used in the paper. Orbital cutoff will be 4.6, and after this you just mention in the properties, as we are just simulating optimization. So initially I will just select the population annihilation, then go to job control and magnesium alloy, and then click on the run button, so the simulations will be run. So I already performed this is the optimized geometry. Okay, and then after this I generated the structure of alanine. This is alanine molecule. You can also generate here in the demol code uh, different organic molecule structure, so you can easily generate it here. Like if you want to generate it here, so you can also generate it in the Material Studio. Just select the pencil tool and select carbon atom, so click here, then here, okay, then click here, so after drawing, just go to right click, display style, and ball and stick model. So you see all the atoms are, I draw carbon, so here are OH and C double bond O. So select this and also this, go to modify and convert it to oxygen. This one is to hydrogen, also this one to so this one to hydrogen, hydrogen, and this one to nitrogen. And now here are two hydrogen with nitrogen, so right click, shift and option button, alt and right click, let move it far away and select it, and then click on the hydrogen, so two hydrogen will attach to this. Then select the carbon, here is the CH3 group, so this is our CH3 group, and then clean the structure. Okay, this will be the alanine structure. Then go to bond order and apply bond order. So now this is a proper alanine structure. So one way is this, if you are generating this, if you want to generate structure in the Material Studio. And the other simple way is go to camera and draw the structure. And camera is I draw here, and just select it and copy and go to Material Studio, create a new page and paste it here. So right click, display style, and ball and atom. So you see that the hydrogen are missing, so click on the hydrogen, so the representative hydrogen will be attached to the respective areas, and then click on the clean. So this is correct this hydrogen, shift alt and right click, and then click the clean button. So this is the alanine. So you can use both the methods and can generate different organic structure. So after this, you just simply use the same method for the optimization of this molecule. Use all those methods as you use for the surface, and just go to control, Java control, and give it name Ela dash OPT, and click on the run and optimize it. So I already optimized this structure. So this is the optimized structure, this one. Okay, now after this, you just simply go to create a new page, and then just simply copy paste the surface. Initially this is the surface, copy it, this is the surface, and then go to the molecule L-alanine and copy this, This is now select this in Shift Alt button and place it to the proper place over the top of the layer. So here the active sites are the carboxylic group, CL1O and OH, and the NH2. So I will directed all these three group to the magnesium alloy surface. So place it over this. If you are confusing in the bond distances, so select this layer and go to display style and select, so the atoms will be small, then you can easily judge the bond distances. So go to the bond distance tool, click on the nitrogen and then this surface magnesium, and then on this and surface magnesium like this, and then hydrogen like this. So it's almost on at proper position, as the nitrogen is 2.14, the oxygen is over the near layer 2.7 angstrom and hydrogen is 1.8 angstrom. It's almost similar, it's almost an equilibrium distance for the optimization. So I'm just selecting this layer again, display style, and I'll select CPK model. Okay, and then make it properly arrange. Okay, if you want to adjust, just double click, and from here you can easily adjust the distances. And now go to calculation and apply all the parameter as I mentioned in for the bare structures. So use all those parameters and just go to here and complex one or adsorption one, whatever you want to give the name. So after this, run. So I already run it and I already performed this simulation. So this is the L-alanine adsorption is already performed, it's already completed. So this is equilibrium stabilized over around about 2.2 angstrom distance from the oxygen and nitrogen side, and from hydrogen it's 2.7 and 2.8 angstrom. So this is the adsorption distances after optimization. Okay, so this is already completed. Select this if you want to present like is presented in the paper. So also select this display style and CPK model. So this is the adsorption molecule over the surface. Click display style. I just want to remove the lattice boundary, the crystal boundary, so I'm not representing it here. So this is the final structure. You can see it's adsorbed properly over the surface. So this is the deep method that how to adsorb the organic molecule over the surface of any alloy. So in the next video I am showing you the plotting that how to plot these simulations, and I will share the PowerPoint slides with you in the group, and I will show you that how to extract the energies and surface charges charge transfer in this study. So I will show you in the next video.